this problem. First of all, Caden was able to see we have I think, was it Caden? Oh, it was Jessica. That's right. It was Jessica. She saw that all sides were equal. So then she made a statement, a very good one. She said, well, if all the sides are equal, then wouldn't all the angles be equal? And I said, well, yes, that is true. So then there's two different ways you can do this problem. If the angles are all equal, can't you take 180 degrees? So 180 degrees of a triangle and divide it by 3 so that they'd be split evenly. Everybody? So this is 60 degrees. Oops, I just moved my triangle. Move back. Okay. So this is 60 degrees. This is 60 degrees. And this angle is 60 degrees. So wouldn't it be true to say 2x minus 3 will be equal to 60 degrees? Is that true? Is that a true statement? Yes. How many of you did that true statement? Anyone? No one. Oh, anyone do this one? Okay. How many of you said, okay, if this angle is 2x minus 3, this angle is 2x minus 3, and this angle must be 2x minus 3. So then it would be true to say 2x minus 3 plus 2x minus 3 plus 2x minus 3 is equal to 180. How many did that true statement? A couple of you? Okay. How many of you just didn't get it right? Okay. All right. So does that make sense though, at least now, everybody? Okay. You'll see that on the homework today. So that's why I wanted to make sure we went over that one. All right. Awesome. Good for you. Okay. Let's continue. All right, so probability is a percent from 0 to 100, which represents the likelihood of an event to occur. So guys, just one more thing. We're finishing up our probability unit. Today's lesson, tomorrow's lesson, and you'll know a lot of probability. So we're doing good. So next week we'll review and test. Anyways, probability, a percent from 0 to 100, which represents the likelihood of an event to occur. So then we talked about these few things in this unit. Independent events. So independent means the first event has no effect on the second event. It has no effect on the probability of the second event. And we know that if that's true, then we can multiply the individual probabilities. So let's look at this one real quick. If we have a blue marble, red marble, and it's independent, meaning we're replacing it, what's the probability of drawing a red and a red? So first of all, on the first draw, I'm going to say, what's the probability of drawing a red? How many reds? 2 out of how many total? 2 out of 3. Questions on that? So I'm going to reach my hand in, I draw out a red. Now I put it back in, starting back from the beginning. So they have no effect on each other. Now what's the probability of getting a red? 2 out of 3 again. So 2 out of 3. So we can multiply those individual probabilities. We're going to get 4 over 9, right? Everybody? If you needed to use your calculator, you could. So 4 divided by 9, and that's 44.4%. So I'm going to round to the whole percent. 44%. Questions on that? Okay, let's do one where it's dependent. This is what we learned yesterday. All right, dependent events. So the probability of the first event occurring will affect the probability of the second event occurring. So for example, we have this bucket. How many total right now? Total is 3. Very good. All right, so now we're going to find the probability of drawing a red and a red. Now the difference between these two is that we're not replacing once we've drawn. So on our first draw, before we've drawn anything, on our very first draw, right now, what's the probability of drawing a red? 2 out of 3. All right, so now we have now drawn out a red. So I'm going to cross it out. We've drawn it. It's on the outside. Now on the second draw, since it's dependent because now we've drawn a red and not replaced it, now what's the probability of drawing a red? 1 out of 2. Good. 1 out of 2. Very good. So now we can multiply those individual probabilities. Now remember, this is the probability of event A times by the probability of event B, given that A has already happened. That's what we learned yesterday. So we'll get 2 out of 6, which is 1/3, which is 33.3%. So I'm just going to go with 33%. Any questions? Do you remember the difference? Do you see it now? Okay, awesome. All right, so then recall, we're going to use this today. That's why I'm going over this. Here we go. Given the set S, this is our sample space, 1, 2, 3, 4, and 5, and given A, a subset, a smaller piece of the sample space, so A is 1 and 3, And B is also a subset, 1 and 4, just a smaller piece of the sample space. Let's fill in our Venn diagram. So in our sample space, there's 1, 2, 3, 4, 5. So on the outside, I have 1, 2, 3, 4, 5. Now I'm going to put these in the Venn diagram where they belong. So I'm kind of going about this a little bit differently than I have in the past. Either way works. Okay, in A, there's a 1. Is there a 1 in B as well? Yes. So a 1 in A and B. So it needs to go in the middle. Now 1 is not in the sample space anymore. All right, let's look at A. A has a 3. Does B have a 3? No, so we've got to place it just in A. Now it's not in the sample space anymore. And then moving on to B. B has a 4. So it's only in B, so it goes right there. And now it's out of our sample space. So left floating is a 2 and a 5. Does everybody understand how I did that? Okay, awesome. Let's answer these questions. What's A united with B? A union B. This is the one that's happy and friendly and welcomes everybody as long as they're in A or B. 3, 1, and 4. Does everybody understand that? If not, say wait. Will you explain further? Anybody need me to explain further? Yes, explain further. Okay. So A united with B means anything in A or B. So anywhere in here or in here is welcome. So the numbers that are in A or B would be 3, 1, and 4. Does that make sense? Yeah. Yeah. Yes, but we place them correctly according to this, right? Does that make sense? We placed them correctly according to this because they both had a 1, so you have to put it in the middle where they intersect. And then in A was also a 3. And then in B there was a 4, but only in B. Yeah. Okay. All right. Now this one, A intersect B. This is the not so friendly one. You can only come into the set if you are exactly the same, where they're exactly the same or where they intersect. So where do they intersect? Our Venn diagram makes it easy for us. We just look right there. There it is 1. Very good. Now understand, guys, at times you're going to just be given this and you're not going to draw a Venn diagram, and you can go ahead and answer these questions anyways. So if we weren't looking at the Venn diagram and we wanted to know A intersect B, we would look at A and B and see where they're exactly the same. So does everybody see how it's 1? The only place is where they're exactly the same. Yeah. Okay. Let's do A complement. So that means everything that's not in A. A complement means everything that's not in A. So this is an A, and isn't this an A as well? Yeah. So everything that's not in A is 2, 5, and 4. 2, 5, and 4. Very good. Okay, any questions on that? Okay, awesome. All right, so let's get to today's lesson. So 3-5, the addition rule and probability. So we've actually practiced this, and you didn't really know you were doing the addition rule, because just like yesterday, when we were doing dependent probability, we were given a formula. I always just did the math behind it instead of actually doing the formula. We are technically doing the formula by doing the math, but I just don't think of it as the formula. But this is the formula for the addition rule and probability, and I'll probably use this a couple times today because this one is a little bit harder sometimes to not use. Okay. So this is the probability of A united with B. So remember that U means or. So the U means or. It's the friendly one. If it's in A or B, it's welcome. So to find the probability of A or B, A united with B, this is the formula. You'll take the probability of event A plus the probability of event B minus the probability of A intersect B, of where it's A and B, the intersection. So I've written this out down here in words just so that you guys understand what's going on here. So I'll give you a couple seconds to write this down. As you do, I'll just explain a few things. Now, we're finding the probability of A union B. When doing this, what we're doing is we're taking the probability since it's A or B. What we're technically doing here is with this formula, since it's united, it's A or B is welcome. Anything in A or B. So we're going to take all of the stuff in A and add it to all of the stuff in B. But now we've got to subtract off where it's in A and B because we can't double dip. If we've already accounted for it in A, we can't account for it again in B. So that's why we subtract off A intersect B, because we'll be subtracting off where they're the same. So we'll be taking off that double dipping. Now, if you don't double dip, and I'm going to do this 2 different ways today, I'll practice this a few different ways, and then you can do it your choice on how you want to do the math behind it. But a lot of times, if you do it the second way I'm going to show you, you'll just take care of this part. You take care of it by thinking about it correctly. So, anyways, you'll see what I mean. I know right now it's kind of hard to see what's going on here until we practice it. All right, does everybody have it about written down? Are we good to practice now? Okay, awesome. All right, so let's go ahead and do our first example here. So it says, using the letters from the alphabet. So what's my sample space? Tell me. The alphabet, right? A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z. All right, so it says event A. Oh, let the letters Joe be event A. So in event A, we're going to have Joe. And then in event B, we're going to have Johnny. So A is Joe, B is Johnny. Okay, so we've got to place these in our Venn diagram in the correct spot. So in event A, there's a J. Is there a J in B?
Yes.
Yes. So it's got to go in the intersection. Is everybody okay with that? All right, so now I'm going to go back to A. There's an O. Is there an O in B as well? Yes, so it's in both. So we've got to put it in the intersection. Then there's an E. Is there an E in B? No, so E is going to go over here. Questions on that? Okay, now we've got to finish off. We have an N, and a Y. Do we list N twice? How many N's are in the alphabet? 1 N. So once we place an N in B, even though there's another N in Johnny, we won't put another N. We've already accounted for N. And then also Y. Okay, questions. Now floating on the outside is the rest of the alphabet, but I'm not going to write that out. All right, so how many, so now let's go ahead and move on. It says find the probability this time of the word Johnny or Joe. Johnny or Joe. Well, first of all, to be able to find probabilities, we need total, right? We always need the total. So how many total letters are there in the alphabet? 26 total letters. Questions on that? All right, let's go ahead and practice this then. So now, if we have a Venn diagram, it's easy. It says find the probability of the words Johnny or Joe. So, or means union, right? If it's in A or B, it's welcome. So how many letters are in Johnny or Joe? So what's the union of A and B? So how many letters? 1, 2, 3, 4, 5 out of 26. 5 out of 26. That's the probability that we'll have Johnny or Joe. So there's 5 out of 26 chance that we'll be able to spell Johnny or Joe. So 5 divided by 26, and that's a 19.2% chance. So if we have a Venn diagram, it's pretty dang easy, right? You can just look in it, combine them, they're united, it's in either. So does that make sense, everybody? So I'm not even going to use the formula. Why make it harder than it is? Does everybody get that? How I just did that? Okay, let's move on to the next example. Okay, so pay close attention to the little details, because I honestly feel like yesterday you guys did not pay attention to the little details, and then you didn't know how to do a lot of the problems. So pay attention to the little details today. So it says, using the ties below, determine the probability of each happening. So determine the probability of each happening. So it asks us, so everybody look, I have this green and red polka dot tie, green tie, a red solid tie, another green tie that's solid, a striped thread, blue, and a blue polka dot. All right, so it says, what's the probability of getting a red tie or a solid tie? Well, we know for probabilities, we need to know totals. So how many total ties here? 1, 2, 3, 4, 5, 6, 7 total. So total is 7. So I'm going to pause there. Does everybody understand what I've done so far? Just total it. All right, so we can do this a couple different ways. We can either, let's do the formula first, and then we'll do it the other way. So event A is red ties, right? So event A is red ties. So now let's find the probability of event A. So the probability of A. What is the probability we're going to have a red tie? If it has red on it, it gets to go. 1, 2, 3. 3 out of 7. Questions up to there. Okay, now I'm going to do event B. Event B, if you read it, is a solid tie. Solid. All right, so now let's find the probability of how many solid ties? 1, 2, 3, 4. So 4 out of 7. All right, now we need, if we're going to use the formula, now we need the intersection, the probability of A intersect B, which means where are they? A red tie and a solid. So where are they a red tie and a solid? So how many are red ties and solids? How many? 1, right? Does everybody understand how I'm doing the intersection? Red tie, the intersection of the first event and second event. So red tie and solid. There's only 1 right there, right? So 1 out of 7. So now we know if you have the formula written down, you take the probability of event A plus the probability of event B minus the probability of A intersect B. So we'll be doing 3/7 plus 4/7 minus 1/7. So now since these all have the same denominator, the bottom of our fraction is the same, we can just add straight across. 3 plus 4 is 7 minus 1, which is 6 out of 7. So the probability we get a red tie or a solid is 6 out of 7. So 6 divided by 7. I'm just going to have us leave it as 6 divided by 7. Do you have questions on how I got that? That's my answer. Now that was the formula way. I'm going to do it the other way because after this example, I'm probably just going to do it the easier way. So I'm going to do it the other way now. So can I erase this real quick? Yeah. Okay, I'm going to hurry quickly and we're going to start back at the beginning and I'm going to go through this way differently because I think it's much easier just to go about it this way. Because then you don't have to memorize any formulas. And that would be nice for this upcoming test to not have to memorize formulas. But really, it's a choice. It's a preference. Okay, so it says, what's the probability of getting a red tie or a solid tie? So if it's a red tie or a solid tie, it's welcome, right? Ors are united, so everybody's welcome. So I'm going to go through and cross out all my red ties first. That's a red tie, that's a red tie, and that's a red tie. Yeah? So those get to come. 1, 2, 3 of them get to come. Now, let's go through and cross out the solids. Now, we can't double dip. If we've already crossed out a solid, we won't count it again. So let's go through and cross out the solids. So that's a solid, it gets to come. That's a solid, it gets to come, but we've already accounted for it. And that's a solid, and that's a solid. Does everybody understand how I did that? I went through and crossed out the solids. Now, how many got crossed out? How many get to come? 6 out of... Wasn't that much easier than doing the formula? Yeah? 6 out of 7. Okay, awesome. Which is 86%. Any questions? So I'm going to probably just do it like this from now on, if you don't mind. Okay, if it made sense, hopefully. Okay, let's practice another one. This bottom one. So I'm going to start over. All right, so now it says, what's the probability of getting a green tie or, they all are welcome, if it's a green tie or a polka dot. So I'm going to go through and cross out my green ties because they get to come. Green tie, green tie, green tie. Questions on that? Now you also get to come if you're a polka dot. So any others in here that we need to cross out? This one, right? So how many get to come? 1, 2, 3, 4 out of 7. So 4 divided by 7, 57%. 57% are green tie or polka dot. Okay. Last one, then I'm going to let you work. Okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And we have these colors here. So what's the probability of getting a blue or an even? So I'm going to do it the easy way. Now pay close attention to the little details, guys. I'm almost going to let you work. I promise. This is the last example. Let's go through it quickly. What's the probability of getting a blue? Well, so we need to go through, since it's or, they're all welcome. If they're blue or even. So let's go through and cross out the blues. That's coming, that gets to come, and that gets to come, right? Now, if you're an even, you get to come into the set. So 2's even, we've already crossed it off. 4 is even, 6 is even, 8's even, 10's even. So how many get to come? 1, 2, 3, 4, 5, 6, 7 out of 10, which is 70%. Questions on that? Okay, let's do another one. Okay, now what's the probability that we're going to have a number greater than 4 or a red? A number greater than 4 or a red. So I'm going to go through and cross out the ones that get to come. So a number greater than 4 would be 5, 6, 7, 8, 9, and 10. Those are all numbers greater than 4. Now you also get to come if you're a red. So any others that we need to cross out? 4. Okay, and then those reds were already accounted for. How many out of 10? 7 out of 10 got to come. So that's 70%. All right, last one. Black. Let me erase this real quick. Black or factors of 8. So I'm going to go through and cross out blacks because they get to come. Those get to come. Now, if you're a factor of 8, then you get to come. So what factors mean what multiply to be 8? So 1 times 8. So let's look. 1 needs to come. 8 needs to come. 2 and 4 are also factors of 8. 2 times 4 is 8. Any others? No. So how many? 7 out of 10, which is 70%. Does everybody see how I did that? Didn't even use the formula. This is almost easier, right? Okay, awesome. Okay, so now do problems 1 through 3. 1 through 3. Have me check them as you go. You can check with your neighbor to see if they get the same answer as you. So looking at this, there was a study that a company did. Hershey's was trying to come out with a new candy bar, and so they did this study because they were trying to decide if they should do milk chocolate, white chocolate, or dark chocolate with this new candy bar. So they tested a bunch of different age groups. So they found that 20% of people like milk chocolate, 30% like white chocolate, and 50% of the group that they were studying preferred dark chocolate. Now here are the age groups. So they had age groups 1 through 16 and older. So age 1 through older than 16. And of the sample, there was 10% were in the age of 1 to 5. 20% of the group was from 6 to 15 in age, and 70% was 16 and older. So now if we want to know the probabilities of the individual of both things happening, we just multiply individual probabilities. So I did 20% times 10%. Now I typed it into my calculator as 0.20 times 0.10, and I get 2%. So I did that. I'm not going to go through. You should know how to type it into your calculator. I'm just going to fill this in. So I multiplied these things. Everybody knows right how to do multiply percents, right? You're sure? 4%, 6%, 10%, 35%, 21%, and 14%. Okay. So it says, what's the probability of getting that somebody was a milk chocolate lover and is 6 and older? So this is where it's an intersection. It's picky. Since this is and, you have to be milk chocolate lover and you also have to be 6 and older. So if I look at my chart, I find the milk chocolate lovers. This is the row, but you can only come if you're also 6 and older. So, 16, 6 and older. 6 and older. Okay, you've got to read it carefully. So it says milk chocolate and is 6 and older. So wouldn't that qualify from here and here? Yep, so it would be 4% plus 14%. 4 plus 14%, which is 18%. Do you see how I did that? Okay, I'm going to change colors. Let's find the probability that they were milk chocolate lovers or is 6 and older. So now notice, same problem almost, but very different. This was and, this is or. So if you're a milk chocolate lover, you get a come. So I'm going to cross out all my milk chocolate lovers because they get a come no matter what. Now it says or is 6 and older. So now 6 and older, anywhere that they're 6 and older, they get a come because or is welcoming. Or 6 and older. So this is also 6 and older. This also qualifies, right? Isn't this in that category? We've already accounted for this one. We've already accounted for this one. But this is in 6 and older. And this isn't in 6 and older. So either of those get a come. So then I would add those up. 2% plus 4% plus 6 plus 10 plus 14 plus 21 plus 35. So 92% prefer milk chocolate or is 6 and older. Does that make sense, everybody? You see the difference between or and and? Were these totally different answers? Even though it's almost exactly the same question. Very different though, right? Do you understand the difference between and or? You have to. And means picky, or means welcome. All right, no questions at all. Okay, then you should be able to finish the worksheet. I want you working till the end of the hour. Do not skip. Notice how I say, do not skip the last page of review problems. I'm going to put some of these on the test to ensure that we're not forgetting old stuff we've learned. So make sure you're practicing them.